Hello again. In this session, I will introduce you to the basis of spectral indices. Spectral indices are a combination of the spectral reflections from two or more wavelengths that indicate the relative amounts of feature of interest. Vegetation indices are the most popular type of indices. But other indices are available for burned areas, man-made build-up features, water and geological features. Using this slide, it is very easy to explain the idea of calculating spectral indices. The diagram shows the reflectance coefficients for the main four classes that can be found on the Earth's surface: water, shallow and deep, vegetation, grass and forest, nature and build-up object. Build-up objects are built from natural materials such as bare soil, like brick, sand, gravel, concrete, so they have very similar spectral response. The coefficients are contended by a curve that show them through the visible, started with green, and near-infrared part of the spectrum. In the previous lessons, we learned how certain objects on the scene reflect the electromagnetic spectrum in the visible and infrared part of the spectrum. Now you can clearly see it through their reflection coefficients. Knowledge of these facts lead scientists to use mathematical combination of create new images of the same scene. The red and near-infrared channels images are mainly used to calculate the vegetation indices. The simplest form of vegetation index is the ratio of the near-infrared and red channels. So two digital images, matrices, near-infrared and red, are simply divided in a raster calculator, and coefficient values for all objects are obtained. The reflection coefficient, and thus the pixel value, for vegetation is the highest in the near-infrared and the lowest in the red region of the spectrum. The reflection coefficient for water is the highest in blue and green and lowest in the near-infrared region of the spectrum. The reflection coefficient for natural and build-up object is the highest in the red part of the spectrum and is lower in the rest, depending on the material they are made of. After dividing the near-infrared and red channels, vegetation has the highest index values and all other objects have lower index values. The results of the build-up index has opposite values. Bare ground and build-up objects have the highest values and vegetation has lower values. Indices are grouped into categories that calculate similar properties. This slide shows a link through which you can additionally and independently reach different types of spectral indices and learn how they are calculated. The most well-known and widespread are the vegetation indices. Vegetation indices are a combination of surface reflectance at two or more wavelengths designed to highlight a particular property of vegetation. Each of vegetation indices is designed to accentuate a particular vegetation property, such as canopy nitrogen or canopy water content in the plant. And on this slide, you can also find a link through which you can additionally and independently research different types of vegetation indices. For the calculation of vegetation indices, the visible red channel, image from 0.6 to 0.7 micrometers, and the channel from the near-infrared part of the spectrum, 0.7 to 1 micrometer, are most often used. On the left is a view of the red channel of the Daedalus system, and on the right the near-infrared channel of the same system. You can clearly see the difference in the display of all objects on these two channels and connect it with the relation coefficient shown on slide 3. Bare land and build-up objects, roads and houses, are bright on the red channel and dark on the near-infrared, while the reverse is true with vegetation. You can also notice how much darker the water is in the near-infrared image, it's black in the darkest object in the image. Let's look at an example of calculating the ratio vegetation index and simple ratio index. The matrix of the near-infrared channels is divided by the matrix of the red channels, that is the pixel values of the near-infrared channels with the red channels, and a visualization of the vegetation index is obtained. The resulting image is created in such a way that the white color is associated with the largest index and the black color is associated with the smallest index. All index values between the minimum and maximum values are graduate and assume grayscale values between black and white. The values in the vegetation indices are therefore interpreted in the following way. All values that gravitate to the white color can be considered vegetation in the image, and all those that gravitate to the black color are not vegetation. Somewhere in between is the boundary between vegetation and all other objects. Where exactly, it depends on the scene. It's not always in the same place. The following example is the calculation of the most used vegetation index, NDVI. As its name suggests, it is about normalizing the index value to the ratio of the sum and the differences of the near-infrared and red channels pixel values. As mentioned earlier, the red channel is mainly used in addition to the near-infrared channel to calculate the vegetation indices. However, for the calculation of some indices, the green channel is used instead of the red one. All mentioned vegetation indices are interpreted in the same way, already described earlier, but they do not show the scene in an identical way. We can see the RVI and GRVI provide more details and better gradation of vegetation areas than NDVI. The reason lies in the fact that NDVI always range from -1 to +1, while GRY and RVI have wider range of index values. Therefore, it can be said that they display indices with a higher radiometric resolution. The next spectral index that I want to present to you is the normalized different build-up index. Normalized different build-up index highlights the urban areas where is typically a higher reflectance in the shortwave infrared region. Compared to the near-infrared region, you can see all this in the diagram on the right side of this slide, where the reflection coefficient for bare soil, water and vegetation are shown. Although it was primarily developed for Landsat thematic mapper sensor, but it can be calculated with any multispectral sensor with a sphere band between 1.55 to 1.75 micrometer and near-infrared between 0.76 to 0.9 micrometer. Here is also about normalizing the ratio, but now short infrared and near-infrared channels. This is what a true color image, RGB, of Zagreb, the capital of Croatia, and its surrounding looks like. Vegetation dominates the picture and build-up objects are barely visible. However, when the build-up index is calculated, build-up objects, bright objects in the image, are much more visible. The build-up part of the city of Zagreb can be seen better, as well as the surrounding settlements. Because everything that gravitates to a wild pixel is assumed to be build-up pixels or bare soil, and everything that gravitates to the black pixel is not. Normalize burn ratio highlights burn areas in large fire zone greater than 500 acres. The formula is similar to the NDVI, except that it uses near-infrared and short-infrared wavelength. This is normalizing the ratio, but now near-infrared channels and short-infrared channels. It also was primarily developed for Landsat thematic mapper sensor, but it can be calculated with any multispectral sensor with sphere between 2.08 and 2.35 and near between 0.76 to 0.9 micrometers. It is possible to create a pre-fire and post-fire NDBR image, then subtracting the post-fire image from the pre-fire image to create a different NDBR image that show the extent of the burn. Darker pixels indicate burnt area. So that would be all for this presentation. Thank you for your attention and see you in the next presentation.